Welcome to today's Explainer. We've got something incredibly exciting on the docket today. Something that honestly feels like a massive foundational shift in artificial intelligence. We are talking about a brand new open weights model from Thinking Machines Lab, and it's called Inkling. If you're at all fascinated by the bleeding edge of machine learning, how we train these massive systems and actually deploy them in the real world, well, you are absolutely in for a treat today. See, Inkling isn't just large, it's astonishingly flexible. We're talking everything from deep reasoning to broad multimodality. But what really sets it apart, what's really mind-blowing, is what it can do to itself. So let's get right into it.
Okay, let's dive into this. What actually happens when an AI is smart enough to fine-tune itself? Because that is exactly the question the developers at Thinking Machines Lab decided to test. They gave Inkling this fascinating, honestly slightly bizarre challenge. They asked the model to fine-tune itself into a lipogram model. What's that? It's basically an AI that completely refuses to ever use the letter E in its responses. Now, normally, if you just prompt a model to skip a letter, it eventually slips up. Well, actually, it almost always slips up. But fine-tuning it to fundamentally alter its own internal weights, that is a whole different ballgame.
So how did it actually pull this off? Well, Inkling executed a complete autonomous agentic loop, basically in 3 steps. First, it literally drafted its own training plan and then generated all the synthetic data and the evaluations it needed to teach itself this weird new behavior. Second, it reached out and used Thinking Machines Tinker API to post-train itself. And finally, this is the really wild part, it successfully evaluated the results and updated its own system to the new weights. The entire pipeline, start to finish, ran in just about 27 minutes. The result? A customized Inkling that successfully dropped the letter E from its vocabulary. It's just a stunning display of agentic coding and autonomous tool use.
Section 1. Meet the Inkling model. Specs and broad capabilities.
975 billion. That is the total parameter count we are looking at with Inkling. It's a giant, right? Specifically, it's a mixture of experts, or MO transformer. But as you probably know if you follow this space, the total parameter count is really only half the story. The real magic of an MOE model is in how it actually utilizes that massive brain.
So while it does have those 975 billion total parameters sitting there, it only uses 41 billion active parameters per token during generation. This is a huge deal. It basically means you get the deep knowledge and the complex reasoning capacity of a near trillion parameter behemoth, but you're only paying the computational cost of a much smaller model. Add in the fact that it supports a staggering 1 million token context window and that the whole thing is fully open weights, and you've got an incredibly powerful, highly efficient engine that is completely ready for massive, complex workflows. Now, Thinking Machines didn't just build Inkling to chase a high score on some narrow leaderboard. They built it to be a true generalist. They trained it natively across agentic tool use, deep reasoning, complex coding, strict instruction following, factuality, and across entirely different modalities. The whole goal here is flexibility. They wanted a foundation model that developers can grab and customize for wildly different real-world workflows. Because we all know those models that look amazing on a benchmark, but then completely break when you try to build an actual product around them, right? Inkling is designed to avoid exactly that. And this brilliantly illustrates how Inkling handles that broad multimodality natively. Instead of relying on these clunky traditional encoders that you just bolt on to a text model after the fact, Inkling is encoder-free for audio and vision. Look on the left, audio goes straight in as D-mail spectrograms, and on the right, images are encoded as simple 40 by 40 pixel patches. Both are processed directly alongside regular text tokens, meaning Inkling can naturally transcribe speech, follow spoken instructions, and do deep visual reasoning on things like charts or diagrams, all in real time. It's literally built from the ground up to just seamlessly collaborate across media types.
Section 2. Effort, calibration, and safety. The cognitive dimmer switch.
You can think of this next feature as a cognitive dimmer switch. Inkling features what they call controllable thinking effort, because in the real world, cost and latency are massive constraints. You obviously don't need maximum brain power to just answer a simple formatting question, but you absolutely need it for complex math or heavy coding. So Inkling lets you turn the effort down to save tokens on easy tasks or crank it all the way up for the hard ones. In fact, when you crank it up, it matches the performance of top competitors like Nemotron 3 Ultra on agentic coding benchmarks, but it does it using roughly a third of the tokens. That is just incredible efficiency on demand.
Now, let's talk about trust. And to do that, let's use a great piece of industry jargon, epistemics. In this specific context, epistemics refers to a model's calibration, its instruction following, and its resistance to censorship.
But what we really mean by calibration is simply the model knowing when to confidently give you an answer and when to just hold up its hands and say, I don't know. Because a model that acts confident 100% of the time, even when it's totally hallucinating facts, forces you to double-check literally everything it says. Inkling was specifically trained to express the right amount of uncertainty. That's absolutely critical for accurate prediction, forecasting, and just plain trustworthiness.
To hit that high level of calibration and safety, thinking machines use this really clever dual grader reinforcement learning system. First, they have a rubric grader checking outputs against a quality checklist. Then, there's a claims grader that actually jumps out and performs agentic web searches to verify the model's factual claims during training. They also baked in abstention-aware rewards. They literally rewarded the model for hedging or just abstaining when it wasn't sure. And the payoff? On the Fortress safety benchmark, it scored 95.9% on benign queries, meaning it properly refuses harmful requests about weapons or violence, but without annoyingly over-refusing perfectly safe everyday questions. A real sweet spot.
Section 3. Under the hood. Architecture and training the giant.
45 trillion. I just want to let that number sink in for a second. That is the number of tokens Inkling was pre-trained on. 45 trillion tokens spanning text, images, audio, and video. It's kind of hard to even wrap your head around. But the sheer scale of data required to build a generalist foundation model of this caliber is just staggering.
So the crucial point is how they actually managed all that data computationally. Inkling was trained on cutting-edge NVIDIA GB300 systems, but to squeeze out maximum performance, they really departed from the standard industry recipes. They used a hybrid optimization strategy, muon for large matrices and atom for everything else. They interleaved sliding window and global attention at a strict 5-to-1 ratio. And instead of using the widely adopted rope, or rotary positional embedding, they went with relative positional embedding because they found it just extrapolates so much better to those massive 1 million token long sequences.
Now, what's really interesting about this slide is the emergent behavior that happened during the massive reinforcement learning phase. We're talking over 30 million RL rollouts. On the left, early in training, Inkling's internal chain of thought monologue was very human, very verbose and grammatical. It's saying stuff like, we need to understand, but look on the right. Late in the RL training, it became heavily compressed and telegraphic. It drops articles and connectives to just spit out, we need determine eigenvalue problem. The researchers didn't explicitly reward it for bad grammar. The model just naturally evolved to drop all that human linguistic overhead purely to become more computationally efficient, while still reaching the exact same correct answers. That is a fascinating glimpse into how AI optimization actually works in practice. Section 4. The smaller sibling. Introducing Inkling-Small.
Now, you would naturally expect a massive drop-off in capability when moving to a smaller model, right? But Inkling-Small practically goes toe-to-toe with its bigger sibling. Looking at the table, on advanced reasoning like Humanity's Last Exam, it scores 29.6% compared to the large model's 29.7%. On hardcore coding with SW Bench Verified, it's 77.4% versus 77.6%. It remains incredibly competitive across chat, vision, and audio tasks as well. Just a tiny fraction of a drop in performance.
So how does it do that? Well, Inkling-Small has 276 billion total parameters, but a remarkably lean 12 billion active parameters. Because it shares the exact same scalable post-training stack and data improvements as the big model, those 12 billion active parameters punch way, way above their weight class. Honestly, this makes Inkling-Small the absolute perfect, cost-effective engine for those heavy, repetitive workloads. Think fast coding, acting as an LLM as a judge, or just churning out mountains of synthetic data.
Section 5. Customizing Inkling today. Where to find and deploy the models.
So where can you actually get this? The answer is right now and almost everywhere. Thinking Machines has made this incredibly accessible from day one. You can fine-tune it directly on their Tinker platform if you want an easy UI, but if you want the full open weights, including the highly efficient NVFP4 checkpoints, they are sitting right there ready to download on Hugging Face. If you prefer APIs, they've already partnered with Together AI, Fireworks, Modal, Databricks, and Base 10. And if you're like me and want to run it natively on open source inference, they have support for VLM, SGLang, and Llama.cpp. They literally built an entire ecosystem on day one to make sure you can actually use and deploy this model however it fits your stack best.
So let's recap. We've seen an AI that can literally write its own code to drop the letter E from its vocabulary.
We've seen a model that can dynamically adjust its own thinking effort to save you money, that natively processes audio and images right alongside text, and that even strips out human grammar just to think faster. The technology is here, the weights are wide open, and the Tinker Playground is ready for you to start experimenting. The only question left is, what entirely new thing will you build with it? Thank you so much for joining me for this explainer, and I hope it sparks some incredible ideas for your next big project.